around the robotic manipulation. So let's start. Last year, I did this presentation for Dr. Petrovich's students in different sections. Now I'm going to go through the sections more quickly, and I start with section number 1. I deleted a bunch of slides, so we are just going to get to the meat of it. In the first part, I'm going to talk about how to represent rigid objects in 3D space. It's basically a linear algebra class. I think the robotics manipulator class could be better described as an applied linear algebra class, because it's all linear algebra. And the second part, we're going to talk about forward kinematics, and in the third part, we're going to talk about the interesting stuff, the inverse kinematics. And I expect from you guys just basic knowledge of linear algebra and basic knowledge of programming. In this case, I'm going to use Python. We are going to talk about robotics manipulators here specifically. I know robotics is a very broad term. When I say robot, I think everyone here in this room will think about a different thing. I'm going to talk about manipulators with rigid links. That's very important. Today you have lots of research on soft robots. That's not what we're going to talk here. Although the theory that I will introduce here can be extended to soft robotics, which is very interesting. They always have a fixed base. They have rigid links, generally motors controlling these joints that connect the links. And generally, we are interested in the position of the end effector, and the end effector is going to do something interesting for us. Move stuff, solder stuff, dig holes, things like that. And it's probably the most used robot ever. Asking everybody, like, where is the ball? Like, how would you answer this question? You could say, well, it's in the wall, right? It's being projected in the wall. But without a reference frame, it's kind of difficult to say where anything is. So I would like to start by introducing the reference frame and showing how it makes our lives easier, right? So now, if we have a reference frame, we can say that, and if we consider that each square is ½ meter by ½ meter in size, we can say that the ball is ½ meter in the x direction. Then here we do a very neat relationship between RGB and X, Y, Z. So red means X, green means Y, and Z means blue. So it's ½ meters in the X direction, ½ meters in the Y direction, and 0 meters in the Z direction. And with this, we can, any equivocation, say where the ball is in space. And I could take these 3 numbers and put, give them to someone, communicate this position in any way. I could make a list, I could make an array, but here we are going to use a vector, and we are going to use a column vector. Why? Because later it's going to be useful. That's why. We could use an array, a list, just use columns to separate them, but here we are going to use column vectors. Oh, we could use line vectors, right? But if we choose column vectors, in the future we are going to be able to do lots of interesting stuff. And here you guys can start to see that all the animations and representations that I'm going to be this is a presentation done in HTML. So this is a web page, and they are all rendered inside the web page. And that's the main difference about the simulator I developed and other simulators. My simulator can be very easily, the simulations can be very easily shared. So if you do a simulation on your computer, you can just send a link to someone and they can open in their smartphone and see what's happening. And it's also very easy to create them. I'm going to show later. And here is how you instantiate a vector using Ybot, which is the name of the simulator I did. You just import Ybot and you instantiate a simulation. You create a list, and then you instantiate the vector object. Everything inside Ybot is an object. So the vector parameter gets the X, Y, and Z positions, and you can also give it a color, and there are other parameters. Of course, everything's in the documentation. And then you just add the vector to the simulation, and when you run it, you have this animation, this simulation. You can do animations later. I'm going to show you guys how. And it's very easy. Like you can do that in an IDE where you install YBot, and when you run it, it generates for you an HTML file. You just open the HTML, and there it is, the simulation. But even if you don't have HTML, let's say you are in a strange computer and you don't know what's installed. Platform. If you guys know Jupyter Notebooks, you are probably acquainted with Colab. Colab, Google. Then if you have a Gmail account, you can open. Let's open a Colab. New notebook. And if you are in any computer in the world with a browser, you can just do pip install YBot. And I need to optimize that. I did this simulator 2 years ago, and since then, every year I tell myself that I'm going to publish it, but I never have time to write the article and publish it. One of the things that I need to do before publishing it is optimizing the installation time, and there are some errors that occur also. So let's wait. In 2 or 3 minutes, it's all done. Yeah, and there are some warnings, and you need to restart the session. I will solve this later. But now if I just hide the output, now YBot is installed. So if I take any code I did in my presentation and copy it and paste it here, and like let's say we want an HD presentation, so it's going to be 1920, I think, by 1080. So, and when I click run, the simulation runs below the cell, and here it is, the simulation. So you guys can see that's very easy, especially in an educational setting. You don't need to, if you want to simulate robots with people that are just learning about mobile manipulators, you don't need to teach them RAWs, you don't need to teach them Gazebo, anything. You can just use this and very quickly go into the most important part of the class, which is the linear algebra part. So let's keep talking about the good stuff. Now it's positioned enough to know where something is positioned in space, and you guys can see that's clearly not, right? They are in the same position, but their orientation is different. So we need to find ourselves a way to neatly represent not only position, but also orientation, and get ourselves what we call the pose, which is position plus orientation. And to do that, one of the ways of doing that is sticking a second referential into the rigid object that you want, and then representing the rotation of the second referential in relation to the first, what we call the inertial referential. There are lots of ways of representing the orientation of the second referential. There's a big use of quaternions, especially in robotics. Euler angles are more commonly in programming in general because they're very straightforward, and we're going to talk about them today. But in linear algebra, using rotation matrices is the neatest way, is the clearest way. There are some drawbacks that we're going to get to it later, but here in this class and in most textbooks, generally the subject is introduced using rotation matrices. So what is a rotation matrix? I promise this is one of the few slides with math, but stay with me. Rotation matrix in this context, in the context of a 3D world, is a 3x3 matrix, and its times its transpose equals itself by times its transpose. So you can change the order of the multiplication, which is unusual, right? Because generally when we have matrices, the order of multiplication is very important. Itself times its transpose equals the identity matrix. So its transpose is also its inverse. And the determinant is always plus 1. You could have rotation matrices that the determinant is -1, but in this case, they would not only rotate the object, but also invert it. And when we have rigid links, we can't really invert them, right? It would be a chiral inversion, like putting it in front of a mirror. And this is how they look like, and we can imagine them like they are putting a new referential in the world, where the new components of this referential, the x, y, and z, are being written in the columns of this new matrix. I'm going to show you guys an examples so you can see that's quite simple. Let's imagine a referential represented by this rotation matrix. It would the x, this column would represent the x, the new x vector, this column the y, and this column the z. So we could take the first column and draw the first column as the first the x vector, the second column as the y vector. Oh, yellow there is not good. And the third column as the z vector. And so in this way we could represent a rotation with this new reference frame that is rotated in relation to the inertial reference frame. I'm going to show you how to do that in YBot. Here I have the same example I showed before. So I instantiate a simulation, create it. I create an array. You guys can see that an NumPy array that is, in this case, is representing that square matrix I showed before, the rotation matrix. Here I'm padding it with 0, 0, 0, 1 and 3 zeros in each side. I'm going to talk more about that later. I'm creating a frame, and one of the parameters of the frame, which is the pose, I'm going to use this modified version of the rotation matrix as its pose. And when I add the frame and run the simulation, I get this nice representation. Now, of course, we can use when we represent rotations with rotation matrices, we are using 9 numbers, right? 3 by 3. But we could use just 3 numbers, which are the Euler angles, and which is generally used, right, when we talk about rotations. But they have some problems. One of the problems that they are discontinuous. When two of the rotation axes align, we have what we call the gimbal lock, which is a problem. And they're not two different combinations of Euler angles can mean the same rotation. So they have a duality there that is not good when we're trying to express something clearly, right? But if we write a rotation matrix that rotates a rigid object in the x-axis, in the y-axis, and the z-axis, like this, we can convert from Euler angles to rotation matrices, and we can combine them. Of course, here is very important how we combine them. Generally, Euler angles are combined from x to z, x, y, z. So we take first we take the matrix x, then on its right side we put the matrix y to multiply, and then on its right side the matrix z. But if we invert it, we have like z, y, x, which is also used. So when you guys see Euler angles, be sure if they're being combined in the x, y, z direction or the z, y, x direction. And here I did an interactive simulation where you can change the Euler angles and see how the referential that is stuck to the rigid body rotates when I change the Euler angles, and how by having different combinations of Euler angles, I can have different rotations of a rigid body. And this is also a way of showing that YBot has also a JavaScript version. YBot started as a JavaScript simulator, and then my advisor convinced me to make a Python wrapper around it, because nobody uses JavaScript in robotics, right? So, but if you want, you can use it directly in JavaScript. This is JS Fido, so there's no Python here. It's just pure HTML and JavaScript. And these elements are regular HTML elements that you can use to create interactive simulations like this one. So let's keep talking about this. Oh, of course, those elementary rotations are implemented in Ybot, so you don't need to write the whole thing every time. You can just use a helper function like that. And we can combine position plus orientation in what we call pose in a homogeneous transformation matrix. I'm just going to call them HTMs, because saying homogeneous transformation matrix over and over gets tiresome. And they are formed by putting on the upper left corner rotation matrix. On each side, we put the vector we created before, the column vector. And below it, we just pad it with 0, 0, 0, 1. And remember that before I padded the rotation matrix I created. That's what I was doing. I was taking a rotation matrix and making it into an HTM. And here it's how I can express the pose of the cylinder using an HTM inside Ybot. So I just put in here the same position I showed you guys before and the same orientation, and I pass it as a parameter to the cylinder object and put the cylinder inside the simulation, and I run it, and here there is the cylinder. And of course we can have the rotations here, but if you want to just change the pose of an object, you don't need to write all the 16 numbers, right? 4 by 4. You can just use the translation helper function, and it's going to give it the 3 numbers you want for X, Y, and Z, and it gives you back the HTM that you need to represent the pose of the object inside 3D world. And now we can do movement compositions, which are something very helpful because they help us to break a bigger problem into smaller parts. So you guys can think of a rotation in the X angle, and you can imagine in your heads how it would mean, how we could represent it with an HTM that represents a rotation around the X-axis, and the same things are around the other axis. And we also can have translations around in the direction of X, Y, and Z, and we can multiply. And by multiplying these matrices, we can compose these movements and do them one after the other. But how should we think about them? That's what we're going to talk later. Let's imagine this movement composition. Rotation on the X. This movement composition is very important. So let's imagine a rotation around the X axis, translation in the direction of the Y axis, rotation around the Z axis, and a translation around a translation in the direction of the X axis. If we just multiply that with math, we always get the same result. But we have two ways we can think about that construction in the 3D environment. We can think about it from right to left. That's what I'm doing there, and I'm going to show you guys how to think about that from right to left. That's how we read it, right? So let's do the first translation. It's a translation in the X direction of 1 meter. So let's do it. So I'm moving our referential 1 meter in the X direction here. Now let's rotate. Let's see, it's rotating pi over 2 radians, 90 degrees around the Z-axis. This Z-axis, see, the inertial Z-axis. And then we do the translation in the Y direction. See green here, so this is the Y, and we do minus 25 centimeters in the Y direction. The Y of the inertial frame of reference, pay attention. Position, right? But there's another way to think about it. Let's imagine we first rotate it around the X-axis. So here we see the X-axis, and we rotate it pi over 4 radians. And now we do the translation in the y direction, but now we do it in the y of the rigid body or the auxiliary reference frame. So let's move it -25 in the new y direction. Pay attention to that. Now we are not using this y direction. We are using the y direction of the frame we are moving. And now we rotate pi/2 in the new z axis. And finally, we do our translation in the x direction of 1 meter. And look at that. We got to the same position. So those are the two ways we can think of our compositions of movement in 3D space. And generally, we think this way, from right to left, as we read it here in the Western world, and always paying attention to the referential we are moving. And that's going to be important later when we talk about basically everything. Yes?
Are there specific use cases for when you would want to use the other's perspective?
I have never seen it. Generally, we do that way, but it's just like tradition, you know. We could do the other way if we wanted to. Of course, we can represent movement in time. We can represent a pose as a homogeneous transformation matrix, like a 4x4 matrix, as I showed you guys before. But if we make each element of that matrix a function of time, we can represent movement in time. So we can animate rigid objects. Here I'm animating just a brick, but later we are going to animate full robots using just this. Here an example using the cylinder I showed you guys before. Here I'm representing I'm doing a translation in the y direction and moving it up and down in the z-axis. And I made the elements being, but of course, they can't be arbitrary, right? The elements of these rotation matrix, they always need to respect what I showed you guys before, these. So I can't choose like, it can be completely arbitrary, but as long as I'm respecting these, I can choose the values and change them with time. And in YBot, what you do is that every object has a method called add anim frame. So you can just pass it the time and the pose of the object in time. And when you do that, you're like creating an animation frame, the frame of an animation. And if you have lots of times and lots of positions, when you put it one in front of the other, you have an animation. And you can go back and forth and play it, and etc. And this is all of the linear algebra I wanted to bring for you guys today. And with this, we can start talking about robots, which is why we're here, right? So let's do it. Let's first talk about forward kinematics. So forward kinematic is when we ask ourselves, what is the pose of the end effector based on the robot configuration? And the word configuration has lots of meanings in systems theory, but here, when we talk about configuration, we are talking about the position of the robot joints. So how much the revolute joints are rotated and how much the linear joints are extended. And some cases are simple, but some other ways are much more complicated. And this is a simple case. I thought I would have a pen here, but I don't, so I try to use my mouse. There it is. Let's see if I can open ScholarDraw here. Where can I get a pen? Here. Yes. So here we see a simple planar robotic arm. And let's say we always know what's the position of its joints. We have a joint on its base and a joint in the middle of it. It's like an arm, right? The elbow and the shoulder. Oh no, the shoulder and the elbow. Yes. And we have Q1 and Q2. So by using simple trigonometry, for example, I know the position of the position of what we are considering here, the elbow of the robot can be expressed the x and z, the x. I will call this position x1. This is the disposition of the elbow. Would be just cosine. Would just be L1 times the cosine. And here I'm going to do something that's very common in robotics. I just write C1 is the cosine of Q1. C1 and Z1 would be the sine times L1. And here again, I'm going to use what we do sometimes in robotics, because sometimes we have like lots of cosines and lots of sines. So if you write the whole thing, it gets very loaded. S1. And now we want to go from x1 to the x final. I'll call it x2, which is here. So now we need to consider this angle. So it would be x1, right? Plus the cosine. Now I need to combine, right? The Q1 plus Q2. And what we do is use that notation I showed you guys before. So it would be L2 times cosine of the first angle plus the second angle. And the Z2 we would follow the same line of thought. So it would be, no, oops. Is this there? Yes. Z1 plus L2 now is the sine of Q1 plus Q2. And you guys can see that in a simple example with high school math, we solve the problem, right? What is the position of the end effector? What's the position of the end of my kinematic chain based on its configuration, on the position of its joints? But when you have like a very complicated robots in 3D, like this one, things start to get much trickier. So a pair of mechanical engineers about 100 years ago came up with of any open kinematic chain, which is called the Dennavit-Hartenberg convention. It's called the Dennavit-Hartenberg convention, but there are multiple versions of it, so it's not a convention. But here I'm going to show you the most common version that I generally see in textbooks, but sometimes they use a different one. And it also, we are going to, here we have like a robotic manipulator, as I showed the images before. Here we have its links and its joints, and we are going to spread over it auxiliary reference frames and go from its base until its end effector, spreading these auxiliary reference frames. And then I'm going to show you guys how we can write a function based on the robot configuration with these auxiliary frames. And this function will give us the forward kinematics. We always start the Dennavit-Hartenberg drawing a line, an infinite line. And the line should be aligned with the rotation or translation axis of the next joint. So for its base, we need to align this line with the rotation of the first joint. This is the first joint, and this is the base. And we always generate at least n+1 referentials. So if we have 6 degrees of freedom here, we have 6 links, and then we are going to create 7 Dennavit-Hartenberg referentials. The first one on its base it's going to be aligned with the rotation of the first link. So it's going to be this line. And the origin point of our first reference frame can be anywhere we want, if it's on top of this line. And the z-axis of our first reference frame needs to be also on top of this line. Now, should it point up or down? It doesn't really matter. When we choose up or down, we are basically choosing what is the positive angle. So if we put it up, it means that when we rotate the first joint positively, it's going to go in this direction, and we should put it down, it's going to go this direction, following the right-hand rule. And of course, the x and y also, they can be chosen arbitrarily, only in this case, the case of the base. I'm going to put them there. Now for the following cases, we are going to put some more rules. As I said before, now we are going to write the Denevit-Hattenberg reference frame for the first link. So first we do the line that is in the direction of the second link rotation, which is now our pink line. And now we need to compare it to the line we created before. And we need to put 2 points. The point of the yellow line that's closest to the pink line, and the point of the pink line that's closest to the yellow line. I'm going to put them right there. Now the point on the pink line is going to be the origin of our new auxiliary reference frame. And again, we can choose z arbitrarily as long as z is on top of the pink line. I'm going to, I don't remember where I put it. Oh, I put it in that direction. The x should always go from the previous line to the line we're drawing now. So it goes from the blue line to the green line. So it should keep going to the green line to the front of the robot. Like this. And of course, following the right-hand rule, if x is in that direction and z is in that direction, the y should be pointing down. So now we have some more restrictions on where to put our reference frames. And we can keep doing that throughout the whole robot. And here I show that this first reference frame, it rotates with the first link, but not with the other ones. As you guys can see, I'm going to play the animation on normal speed here. So when I rotate the first link, it goes with the first link. But when I rotate the rest of the robot, or I move any other joint, it should stay static. Now, draw when we are making the referential for the second link, we draw our line on the rotation axis of the following link. So the line would be here, and we compare it to the previous line we created for the previous link. And now the closest point is whatever point we choose, because they're parallel, right? So we can arbitrarily choose whatever point we want. Of course, it would make more sense if we choose something right in the middle of the robot, so it would be easier to draw. So we can create something like here. Again, the z axis need to be on top of the pink line. Again, the direction you can arbitrarily choose. A simple way of choosing is just sending a command to the robot. Send a positive command. If the robot goes like this way, you draw it like this, and if the robot goes the other way, it draws like that. There's the z. And now, based on what I said before, do you guys think that the x-axis points up or down? Anyone? Up or down? No one? Well, it should go always from the direction of the previous line to the line we're drawing now and continue going. So it should be upwards. Let me go faster. And again, following the right hand rule, the Y can only have one direction. It's this one. And I'm not going to keep doing that. It's quite boring, I know. But if we do that throughout the whole robot, we keep doing this, following this algorithm, and go until the end, we have all of the Dennett-Wittenberg reference frames. And you can think to yourself, like, great, how do I get the forward kinematics from them? Well, when you follow this, this algorithm, you get a way of writing one referential in relation to the previous referential, always as a rotation in X and a translation in X, and then a rotation in Z and a translation in Z. Always like that. So first we do the rotation in Z, and then we do the translation in Z. So it goes up, and now we do the rotation in X. So it's going to rotate around the red axis. And now we do a translation in X. And now they coincide. And we can keep doing that from bottom up to the top. Always the same translations. And you guys can see that, like, some translations, they depend not only on parameters of the robot, but also on the configuration of the robot, right? Because like this, the rotation in Z, this rotation in Z, it depends on the rotation of the first link. So depending where the first link is, the rotation is different. And if we keep doing that, we can go from the base to the end effector. And we have ourselves a long list of matrix multiplications that works for us as some kind of forward kinematics function. And this is like the most straightforward way of finding the forward kinematics of any opened kinematic chain formed by rigid links. But when we use a robot, we generally we are interested in going somewhere and doing something, right? So a more interesting problem is not the forward kinematics, that's where we should start, but the inverse kinematics. For example, if something is in a pose that I know what it is, how do I put my robot there, get it, and move it, right? And that's the last part of my presentation, which is the inverse kinematics. Inverse kinematics is when we ask, what is the robot configuration based on the pose of the end effector? And I'm going to show you very quickly how we can solve it for the simple case, which is the planar robot case. And you guys can see that it gets very convoluted very, very quickly. This is the model of the forward kinematics that I created with you some moments ago. And now let's try to invert it. Instead of putting the 1 and 2's inside the functions and getting X and Z, let's try to get the function for the 1 and a function for the 2, and a function that we put X and Z, and we get the 1 and the 2. So what I'm going to do is something very arbitrary, but it will make sense. I'm going to square both sides and sum them. And then we can isolate the cosine of Q2. And using inverse cosine, I can get Q2. Now we have a problem, right? Because the cosine of plus 30 degrees and cosine of minus 30 degrees is the same. So in this case, I'm choosing the positive Q2, but we could have chosen the negative Q2. It wouldn't be a problem. We would just get another configuration. Here is the model in matrix form. Here, what I'm writing here is the same that I wrote in the first slide. It's the same thing, but in matrix form. And I'm going to put this here in the true position. So everywhere there's a true, it's Q2, and I'm going to substitute it. And now I just need to find Q1, right? But you can see that it gets very, very big, very, very quickly. And then I get C1, that expression for C1 and that expression for S1. And if I have the cosine and the sine, I just use the arctangent and I can find the Q1. Of course, the arctangent function, it has a duality, right? Because we don't get the direction. And here the direction is very important. So I'm using arctangent 2. And here I'm solving the inverse kinematics problem using Ybot. In the case where we have a long kinematic chain, it's basically useless to use straightforward trigonometry. It would be very, very hard. So there are lots of things that can be used in this place. There's an active community of people that research better ways of doing inverse kinematics, and I'm going to talk a little bit about how inverse kinematics were implemented in Ybot. This is how you can write it. So here I'm creating two robots. Why? The first robot represents the initial position, and the second robot represents the final position that I want to put the robot in. That's why the second robot, the second robot has an opacity of 25%. So it's just like a ghost of the past or something like that. I put the two robots in the simulation. Here I choose a target. The target is going to be the pose of the robot after I calculate the inverse kinematics. And it's going to be the robot forward kinematics, so the position of the end effector of the robot now, multiplied by a translation in the z-axis. And this translation is of minus 30 centimeters. So it should go down 30 centimeters in the z-axis of the world, of course. So here I get the inverse kinematics result. I just use the method inverse kinematics that every robot in Ybot has. And I give it a target, and it calculates the robot configuration based on the pose I give it, based on the target. And here I'm animating, very simple animation. So I create a loop, and this loop goes from the initial moment to the final moment. And what I do is that I start to diminish the original robot configuration. So this goes from the initial value to 0, and I start to sum the final robot configuration. This value goes from 0 to 1, and so at the end this goes to absolute 0, and this goes to the final value. This is not the smartest way of doing it, but it's the simplest. And then every time I loop, I add an animation frame to the robot. So I add an animation frame, I give it a time, and I could give it a pose of its base, but here I'm just giving a different configuration. And when I run the animation, I have this animation of the robot moving. And you can imagine that, like, if I can, this mouse is a bit tricky. No, that's not what I want. And you guys can imagine that if I can animate the robot going from its initial position to its final position, I could also send commands to a real robot and slowly change the configuration of its joints and make it slowly converge to the place where I want it to converge. And when it gets there, it can do what it's supposed to do. It can solder something, it can grab something, and etc., etc. Now I'd like to talk a little bit about this magic function, the inverse kinematics function, and what it's doing here. I talked a lot about like kinematics here, but there's also I talked about inverse kinematics, but there's also differential kinematics. Differential kinematics, I'm trying to study the relation of the speed of the robot, the speed of the end effector in relation to the speed of the joints, or the contrary. If I know the speed of the joints, what is the speed of the end effector? This would be the forward differential kinematics. And we could also get the dynamical kinematics. So based on the force or the torques applied to its joints, what is the force being applied in its end effector, or based on the force of its end effector, what's the force I should apply on its joints? So as I showed you guys before, let me open ScholarDraw again. Is it still here? Yes. we can create a big function dependent on Q. And this function gives us the pose of the end effector. We can create this function using the Dennett-Wittenberg parameters and the translations and rotation that I showed you guys before. And from that, we can extract like a vector. The x, y, and the z. And I will call the Euler angles alpha, beta, and gamma. And I showed you guys before that we can take these Euler angles from the rotation matrix that we get from this, from a function. So this is like a function that's not based only on the configuration. Whoops, what am I doing here? It's like, let's say we get we have the forward kinematics function. And the forward kinematics function we did with Dennett-Wittenberg before. It depends only on the configuration. And then we can apply another function that makes it takes the homogeneous transformation function, the homogeneous transformation matrix, which is 4 by 4, so 16 terms, and it makes it into this column vector, which is x, y, z, alpha, beta, gamma. And but this transform that function is constant. What can change is the configuration of the robot, so we can rewrite it as just one function. Q. And now, when we start to talk about differential kinematics, we start talking about the rate of change of Q. So Q can change with time. So if we derivate both sides, we can have a x dot, x, y dot, and z dot, and also alpha dot, beta dot, and gamma dot. See how much more? Yes. And that would be equal to this, to the derivative of this function, that itself is a function of the configuration, but now the configuration is a function of time. And you guys may remember that, like, when we have the chain rule, right? So we have f of g of x, for example, and we derivate this we differentiate it in relation to x. We have the derivative of x in relation to g and not to x, right? Times the derivative of g now in relation to x. This is like for the unidimensional case. X is just a scalar. Yeah. Here we have a matrix. So this function now, it's a matrix itself, and we call that the Jacobian matrix. And in this case, this is the geometric Jacobian. Times, I'm going to call Q dot the column vector that represents the configuration of the robot. So it's a column vector with where Q1 is the joint 1 and so forth. And this would be the kind of differential equations we would be solving in differential kinematics. And here I'm solving a similar equation, but I'm solving the equation in function of the task function. the concept of test function is a function that's zero only and only when the function is done. So if I write a function like this, where I have an R of Q, where Q is our configuration, and I have the X, desired X, which is an input of the function, minus the X the robot is now. Where can we get this X in function of the robot configuration? Well, it's from the forward kinematics that I showed before. So if we write a function like this, and we keep doing that for all components, and finally we end with the desired gamma, we call it gamma dash, minus the gamma q. Do you guys agree with me that like this is zero only and only if the robot arrives to the desired position, right? Because it's like the robot actual position minus the desired one, so they only will be zero when they coincide. This test function has some problems, it has some discontinuities, but generally it works. There are other proposed test functions that work better, but I'm going to present only this one today because it's the simplest. Now, from the study of differential equations, we know that every time we write a differential function, f of t, differentiated in relation to t, and we write it in a way that this is equals to minus k f of t. It's very easy to prove that f of t is always the exponential of minus k, no, I'll do some silly k like this, minus k t times some initial value, the function on the initial condition, right? So, and if k is positive, I can be sure that this is going to converge to zero, right? Because as t goes to infinity, the exponential goes to zero times the initial the value of the function in the initial condition. I get it to zero. So if I can write my task function in this way, and this will going to convert to zero. So converting the task function to zero means that I get the value, I get my task done. And if I get my task done and I get the configuration of the robot when the task is done, then I get the configuration. I solve the inverse kinematics problem, right? Because I get the configuration of the robot when the robot arrived to the position, to the pose I want him. So I can try to write this function like the derivative of r, and r itself is a function of q, and q itself is a function of t, right? Because the configuration is changing with time. Will be equal to minus k. K is a constant that I can choose arbitrarily, times r of q of t. Now I will find another Jacobian here, which is called the task Jacobian, another Jacobian very important in the study of robotics. So I will have the derivative the same way I had this geometric Jacobian in the differential kinematics. I have a task Jacobian here. The task Jacobian will be represented like this. And here, this is very weird, right? Because we are dividing by a vector, but there's no division by vector, not that is defined in linear algebra. So this is like an abuse of notation, but you guys know what I'm talking about, right? It's the Jacobian. This will mean the Jacobian times q dot. Q dot will be the derivative of q in relation to t, equals minus k times r q t. So if I invert this matrix and write this, This is a constant, right? So you can put it in front and put the Jacobian here. The Jacobian again is this, but now is the JT, the test Jacobian, times R QT, and this is a big problem because we are inverting a matrix. Inverting a matrix, especially a big matrix like that one, is a very, very big problem. So what we do is we generally use the pseudo inverse. The pseudo inverse is a concept invented by Roger Penrose, and like when we multiply a matrix by its inverse, we get the identity, right? But some matrix, they don't have inverse. So we multiply by the pseudo inverse. The pseudo inverse, we get something very close to the identity. It's as close as possible we can get to the identity, but not the identity itself. So sometimes we need to, so that's what I implemented here in YBot. It's the pseudo inverse of the test Jacobian. And now we have a differential equation, right? And if we solve this differential equation, we get Q. So if we just like integrate on both sides, integrate Q dot, we get Q. And if we integrate minus K of J times JT times our test function, I just write RT, or the test function. If we integrate both of them in time, so dt, I don't have space, but imagine a dt here and dt here, I get the result. It's a very hard integration to do analytically, but if we use some numerical method, like first order Euler, we get to the result quite quickly. So that's what I'm doing here. It takes some time to calculate the inverse kinematics because it's iteratively getting closer to the result. And the more I let the first order Euler run, the closer I get to the iteratively to the result. And that's why sometimes I can get slightly different results because it's iterative, right? So it depends on how much I let it go. And that's basically the whole first part of a course on robotics manipulator that I condensated in about an hour. It's a lot of information. So if you guys want to know some more about YBot or robotic manipulators, I should just go into the YBot documentation website. Here in the theoretical reference, there's everything I talked about. And here in the home, we can see like how you can pretty easily embed the robotic simulations done with YBot inside a web page. And you can it's like an interactive 3D video, right? So I imagine this would have more applications in rigid body physics beyond robotics, right? And if you guys want to learn how to use the JavaScript version, just click here, or the Python version, and there's a tutorial. And of course, I didn't show how to catch stuff, right? What you do is that like when the robot is on the position that it's about to catch the rigid object, you use this function, which is attach object. And what it's going to do is that it's going to start to calculate the position of the rigid object, in this case, the cube, not in relation to the inertial reference frame, but the reference frame that it's on the end effector. So it's just going to keep the same position. So there's no physics involved. It's just the relative position is going to be kept the same until you call the second function, which is detach. And then in this way, you can simulate attaching and detaching things to the end effector of the robot, like it's being done in the simulation, where I use a SCARA robotic manipulator to manipulate that cube from left to right. And that's pretty much it. From here, what a robotic manipulator course would do is start talking about dynamics, and we could start talking about like what is the torque we should put in the joints to get the specific force in the effector, or vice versa. And for that, generally we abandon Newton and start using Euler-Lagrange equations, and we start using some nonlinear control techniques like feedback linearization. I don't know if anyone here has any control background, and some more interesting things. So, but I don't have time to talk about this today. I'd love to one day teach this at a graduate level. And that's it. That's a lot of information. So, does anyone present here or anyone on the internet has any question?
So, yeah, also recording it. You guys are recording by cross section, like see the game detail, and we also doing documentation. Like that. So I know that this forward kinematics problem is very important, but the configuration of the robot to get to a specific code, but the other one is not configurations.
It depends on the degrees of freedom, yeah, of the robot. Exactly.
Instead of solutions related to this method.
Mhm. So if the degrees of freedom that you're trying, if the degrees of freedom you're imposing on the pose of that you're trying to reach, and in 3D space we have 6 degrees of freedom, right? X, Y, and Z, and pitch, yaw, and row. Pitch, yaw, and row, exactly. And the robot has 6 degrees of freedom, right? In this case, degrees of freedom means joints. So in this case, when I run the program, it's always going to convert to the same pose. Let's say it's always going to get close to the same configuration. But if I impose less degrees of freedom, for example, if I'm interested in putting the manipulator in an X and Y and the Z, but it does not matter what is the angle that I get when I go there. Then there's a much bigger ways that you can approach the position, and every time you run the inverse kinematics function, it's probably going to give you a different result.
Another issue is the issue of some constraints that you want to the robot that over value that it doesn't meet
That's a very fertile field of research in robotics manipulation. My advisor do his research exactly in that point, and he uses optimization techniques. So he imposes optimization restraints to the solving of that equation, and in that way you can avoid walls or even avoid people, collaborative robots and things like that. Yeah. Yeah, this in this iterative method, the way it's done here, no, it's just going to get you a position, but it's not going to think about how it's getting there. So it's not going to try to deviate from anything. But my advisor sent me some simulators, some simulations done in Ybot about a paper he just published, and he's doing exactly what you're saying. Let me see if I have it here. Yes, he published a paper, and in the paper there's the link, and you can click on the link and see what he's doing. It's, I think it's this one. In this one, he's imposing some optimization constraints. Oh, yes. He's imposing optimization constraints to the movement of the robot arm. And the robot needs to get from point A to point B to this pose, but it can't touch the wall. And in the technique he proposes in the paper, in finite time. Some optimizations that are interactive, you can do that in finite time. And there are also some geometric computations related to the positions of all the links, and that's something that he's a specialist on, and I'm not really. Yes, he has also that in using the real robot.
Maybe some perfect model, maybe some commercial robotics.
So especially in robotics, we are very lucky in robotics manipulation because the models are very good. Because
Okay.
yeah, it's not in their case with mobile robots, right? But when we build a robotic manipulator, the base is fixed, so and all the parameters are imposed by the people who build it. So the models are very good in this case.
Then, you know, how we do it.
Generally, no. Generally, one-shot transfer is enough.
Do you know what type of methodology is used here?
I haven't read the article, but the article is let me see. Let me let me copy this. Oh, there's the DUI here. This is the article. Smooth distances for second order kinematic robot control. Basically this. And basically in here he's solving that the same problem I showed you guys before, but I'm solving it using just first order Euler integration, which is like the simplest method to integrate something numerically. And here he's solving that not only with first order Euler, but also imposing some optimization constraints. And of course, like the Ybot's not only limited by robotic manipulators, right? In this other is also an article my advisor wrote on the control of drone swarms. And here what he did was an interactive way of showing the pose of all the drones, right? Because in a video, you can't really look around and see where the drone is. But if you record the position of the drones and you save them in a file and then you plot them using spheres inside Ybot, inside Ybot, you can stop time and then move the position of the drones and see if they hit or not. So here, that's why he's using Ybot here. Here we see like the whole path of the drone around the barrier. And here he's using an extension of artificial potential fields. It's something very common in mobile robots. But sometimes in artificial potential fields, what you get is to a local minima. And in this technique, he's proposing I think in the beginning, in this technique, he's proposing you don't get local minimas around the obstacles as you would when you directly use the originally proposed artificial potential fields for robotics. And you can also use it for manipulators, of course, but here he's more involved in the path of the and the factor around the obstacles. But of course, you can use that with any moving thing. In this case, he's using drones also. Very interesting stuff. Yeah. Very interesting. So let's see if I have Calibro. So when we have artificial potential fields, let's say we want a mobile robot represented by this dot go from here to here. So we would have a potential field kind of pushing the robot towards this position. So it would be like a field like this, and we can take there are more interesting ways of doing this, but we can take the velocity command, like the twist command for the robot, as this arrow in the potential field. So if we just leave the robot here and follow the arrows, the robot will get here. But let's say we have we have Mhm. There's an arrow. Mhm. Yeah. So as Professor Petrovich explained, we have like a field of arrows. This field of arrows is the attractive ones are created by where I want the robot to go, but I also want the robot to avoid So let's say this is a barrier, and the barrier would create around itself another field. And by summing, doing a vector sum of both of these fields, I would get arrows pointing the way, let's say. And if I use these arrows as the velocity command of the robot would go here and be repelled by the barrier and get to the objective. But if we have an objective here, we would have around here an arrow pointing like here. And if we have an obstacle here, in the same position, we have an arrow pointing the other way, and they cancel. So when the robot gets there, he thinks he should be there because the two vector fields are canceling each other, and so the robot does not move. It gets to a local minima. See, and in this different where's the article? Oh, I think I closed it. Well, I closed it, but in the potential fields extension, my advisor suggested when you get situations like this, you just create an auxiliary field that will guide the robot around the obstacles. That's basically it.
Simple matrix, but think about you like comment to your simple
So why bot is extendable? We have a lot of robots. Let's see if they work here. In the robot gallery, we have some robots available in Python. And their simulator being extendable, it means that we can add other manipulators. And if your manipulator, I think it's open source, right? So the Denabit, if the Denabit Hattenberg parameters are available, we can put them in the simulator and create other robots and put it here. And when I solve the equation, we get like we have the twist. This we have like we can have the actually in a this would be the control. This would be like a control signal to the robot, right? So we could run the simulation inside YBot and take these control signals and publish them via ROS. And everything is in Python, so we can put them both in the same script, right? Run them continually together, and that way we could see on the screen and on real life the two things happening simultaneously.
Obviously, you are right?
Mhm.
And how are those values that are inside there?
Denabit Hattenberg are also inside the URDF, but the URDF has not only kinematical information, but also dynamical information. So the inertia matrix that represents the inertia of all the links is also inside a URDF file. Yeah. So you cannot, so you don't have.
Say, doesn't have some loose constraint.
Oh.
Because you can put it here, it's not
Mhm.
according to the convention storage. Or is there always following?
I have never seen one that was not following the convention. But as I said before, there are different ways of using the convention. So probably very confusing. Generally, the different ways is in relation to the x axis. As I said, the x axis in the convention I showed goes from the first line to the second, but some people point it from the second to the first, and that invert a lot of transformations that makes things more complicated. Mm-hmm. Yes, I can show my email in the presentation. I think it's No, my email is not in the presentation. I should have put it there, but it's my two first names, Jonathan Ryan @gmail.com. Let's see what happens. I never Googled my email. Well, some old stuff. But that's my email. If you guys look at the video, it's going to be there. And if you guys have any doubts, just ask me. Of course, we have a GitHub, so you guys can open issues on GitHub and ask questions there. We are very active. Yeah, take it easy. Yeah, you're welcome. Thank you, everybody. Oh, I think there's a... Yeah. Oh, perfect. Yeah.